And hello, everyone. So I'm Tanguy Lunel. I'm a researcher at France Energy Marine. I'm an atmospheric modeler. And I joined the NEMO project 4 months ago now, mainly to work on the characterization of atmospheric, mainly using models. Can go to the next slide. So to recall some context, I have to recall that obtaining reliable turbulence information is still rather difficult for the wind industry. And one strategy can be to use LiDARs, as Maxime presented, and in this aspect, next slide, in this aspect, then the AROM model can be an example of what can be used. So AROM is the fine resolution numerical model used by Meteo France. And it has the advantage actually of having internally turbulence estimator called can then be used for turbulence estimation. And that was also the model that was used a few years ago by the DGEC and Meteo France in these wind turbulence characterization studies that they made in the main tender areas of France. And these reports are very interesting, I think, for the wind industry. But if you look like really into into the methodology of these reports, you can find this sentence, for example, well, stating that first the comparison between AROM and the meteorological mast is rather good, but however, the results are mixed for the LiDARs, for the comparison with the LiDARs at sea. But this is not clear whether this is due to the behavior of the AROM model or to a problem with the quality of the LiDAR measurements at sea. So that's the NEMO project. It's important to study also the model part. And looking again at the AROM model with an example on here, it's a profile taken from AROM in blue and from the LiDAR in black. We can see that above the Plany Island on a specific date at a specific time, AROM is rather well able to model the wind speed and the wind direction. The estimation of TKE is not good at all. The TI retrieved from that is only half of what is measured by the LiDAR. So seeing that, we can state that we definitely need to better understand how the weather models behave in terms of turbulence, specifically over the sea, because most of these weather models were first deployed above the land where most of the observations are available. And so the first step to better understand the behavior of this weather model is actually to try to better characterize the spatial variability of turbulence from the coast towards the sea to the offshore. And then once we'll have better understand this variability of turbulence, we'll also try the modeling of atmospheric turbulence with models. So to study this, my methodology in NEMO is mainly model-based, based on Meso NH. That is a research weather model largely used in the French community of the atmospheric science. And that's also the research model that is used for the development of AROM. And with this model, situation in two main sites. So the first being the Plany Island that Maxime already presented you. And a bit later in the project, we'll also study situation at Blythe in the North Sea in collaboration with Fraunhofer. And so on both of these sites, we have also observations that will enable us to compare the model outputs with the observation and to validate each other. So to present a bit the Planier Island, this is a figure coming from the paper of Maxime Thiebaud. And I just want to give an overview of this site that is located in the Gulf of Lion in the Mediterranean Sea. So that's an area where until recently we didn't have much information on the wind turbulence characterization. And that's quite a specific area in terms of wind, well windy area, mainly because of two main winds, the Tramontane and the Mistral, that are mainly driven by the mountains around, meaning that these winds are really channeled around the mountains. And actually, when you look at the wind rows on the right coming from the Planier Island, you realize that really you have only two main directions, either northwest or southeast, and rows in locations where there are mountains, and that mountains is actually channeling the flow around it. And considering this this direction, this northwest direction, for example, we can consider that the Planier Island is about 15 kilometers away from the coast, which is about the same than the first pilot wind farm that's being installed in the Mediterranean Sea. So on presented the wind profiling LiDAR that's been installed with a sampling rate of 1 Hertz, and that's able to measure the wind from 60 to 220 meters above the sea level. And in combination with this observational data, we have the model data. Next slide. So for the model part, I use Meso NH. So as I already said, model, non-hydrostatic, and one advantage, one asset of this model is the fact that it's able to run simulation at the mesoscale, meaning the medium resolution, or also at very fine resolution, like what we call large eddy simulations. And to present you some preliminary results, I will present you some at the beginning of January 2023. You have a wind map on the right with the color corresponding to the wind speed, and you also have the barbs corresponding to wind direction and speed. With in white is the coast. You can actually read the Marseille sea location and the Planier Island location as well. In this situation, it's a northwesterly flow, so it's a kind of mistral, but which is not so strong. And to keep in mind that actually the atmospheric properties that we'll find over the sea are much influenced by the upstream condition, meaning the condition of the atmosphere above the land. And so this result, well, this wind map I show you on the right is retrieved from the mesoscale model at 1 kilometer. But we know that this kind of model is not well able to model turbulence. So next slide, please. So that's definitely a shortcoming of the mesoscale model that cannot explicitly resolve the atmospheric turbulence. Atmospheric turbulence is mainly characterized by like big eddies in the wind of about between 1 kilometer and 200 meters. At 1 kilometer resolution, then you're not able to explicitly solve the equation that will represent this. We use in this case so-called parametrization. That's a way to derive the turbulence from the other characteristics of the flow. But if we want to have really a model that is reliable in terms of modeling of the turbulence, we need to refine the resolution. So that's what we call dynamic downscaling. So we'll take the model at 1 kilometer on the left, and then downscale it to 200 meters and then 40 meters. at this resolution, then we'll be able to model the turbulence of that are actually inside the flow. Next slide. So from the model, then we can obtain this kind of TKE maps. So in color corresponds to the total TKE modeled by Meso and H. And what we see here is that on the left at 1 kilometer, we lack turbulent kinetic energy in comparison to the model, to the large eddy simulation that is located on the right at 40 meters. And next slide, please. So if we take a look at given time step among the situation, here on the left is the wind speed that is modeled by the Meso NH LES. And we really see this kind of eddies that forms above the sea, that therefore coming from northwest. And you see that after the coast, a few kilometers away, the flow starts to create big eddies, and that's what will then feed the rest of the turbulent kinetic energy above the sea. Next slide. Well, then I had a slide with an animation, but it doesn't work. So it was just to show along the day, but I guess afterward. And next slide, please. And so what I showed you until now was maps of TKE seen from above, but we can also, thanks to the model, look into the model by doing cross sections between the coast and the sea. So the cross section is actually seen in red, with the line in red on the left here, from the coast to the Plani Island, and in speed field on the top right corner, going on the left from the coast to the sea. And what we see is that actually, as we go above the sea, little by little, we see kind of rolls that's actually thermals that going from the sea and to higher in the atmosphere, meaning that really this part of the atmosphere is unstable, big eddies, and then feed the rest of the turbulence. And in the lower right corner, then we see the TKE, with the TKE that overload the land on the left is mainly driven by friction of the land, and then over the sea, it's more mainly driven by the thermal properties, thermal exchange between the sea and the atmosphere. Yes, we can be we can be more confident in what is modeled, in the sense that we're really able to model physically meaning processes and to resolve the turbulence. And we can try to compare it with the LiDAR data. And what I show you here is that first, the model in red at 1 kilometer, well, is not performing well in terms of turbulence kinetic energy in black, but with the LES in green, then we improve our modeling of turbulence. And next slide, please. And if we decompose the different components of the TKE, like the vertical component and the horizontal component, we can also have a kind of critical view on the LiDAR, because actually what we see, the vertical component of the LiDAR have this kind of increase above 200 meters, and this kind of increase in TKE is not really physical and is never really comparable to anything that we can see in the LES. So this LES also allows to have a critical view on the wind profiling LiDAR, and specifically it seems to indicate that data depends on the height as well. Next slide, please. And here on the right is maybe a bit more technical in terms of modeling, but Actually, in the field of atmospheric modeling, we also discuss mesoscale and LES modeling. And LES is often like seen as the best model you can have, right? But models claiming that they are LES at rather coarse resolution. And in the atmospheric science community, we define an LES from when we manage to resolve explicitly in the model at least 80% of the TKE of the turbulent kinetic energy. And what I show you here on the right is that actually between the sea level and 130, the resolved TKE is less than 80%, so that even at 40 meters of horizontal resolution, this is not an actual LES. So just to say, well, then it depends also on the atmospheric situation, etc. But just beware of what we call LES sometimes. So-called LES are not actually LES. Next slide, please. And so these were just very preliminary reasons. I'm working on that. And so far, we can tell that mesoscale simulations are not able to well capture the dynamics of turbulence over the sea in this type of coastal areas, specifically in Mediterranean Sea. But large eddy simulation allows to better model this turbulence. But still, this kind of simulations are very expensive in terms of computation time. So the goal would be so has to have something that is more interesting for industrial, but that's still able to well capture the dynamics of turbulence in the mesoscale model. Next slide. So the next step is actually to generalize a bit what I showed you to typical weather situations. On the Mediterranean Sea, I've run a K-means classification to have different clusters. Then I will run an large eddy simulation for each of these situations, and then use these results as references for trying to improve our understanding of what's happening in terms of spatial variability between the coast and the offshore, and also to try to improve the modeling of turbulence in mesoscale models. And after the summer, after the NEMO measurement campaign that will be we'll be able also to model cases in Blythe on the North Sea and to collaborate with Fraunhofer to try to improve again our model. Thank you very much for your attention.